All right, welcome everybody. In this video, I want to walk through how we can find the line of best fit using matrix operations in R. So a line is going to have a formula in general, y is equal to a plus bx, where a is the y-intercept and b is the slope. So A tells us the initial value of Y when the predictor variable X is equal to 0, and the slope B is telling us the rate of change. If I were to increase the value of X by 1 unit, approximately how much is the response variable Y going to change? So let's suppose I have n paired points in my data set. So I've got x1 so x is my predictor variable, y is my response variable, and I've got a set of n of these points. And what I would like to do is figure out which line of the form y is equal to a plus bx best fits the data. And so, for example, let's consider the storms data frame in the dplyr package. We've seen this earlier, but this contains almost 20,000 observations for storms that occurred in the North Atlantic since 1979. And there are two variables of interest in this data frame that we'll think about. So we'll think about wind and pressure. And how can we use a storm's pressure to predict the wind speed of that storm? So here I'm going to think about pressure as the predictor variable. If I know the pressure, can I use that to predict the wind speed at the center of the storm? So so first let's just kind of take a look at what the data looks like. And if you want to run this code cell, just be sure that we're using the dplyr package and we're using ggplot. So you'll have to load the core tidyverse packages. We ran the library tidyverse command earlier in this notebook, but you'll want to make sure you load those packages. And once you've loaded the tidyverse, this code cell should run just fine. I think I've loaded it. Great. So here you can see what a scatter plot looks like. So yes, there's definitely lots of physics involved in the wind speed of storms and how that relates to pressure. So what we can see is as the pressure rises, the wind speed declines. So when a storm has really low pressure, that actually corresponds to having high wind speeds, a stronger storm. So we can see that the data lines up very strongly in a linear pattern here. So what is the formula for this line in blue? Like what formula best fits this line of data? So you can imagine there are lots of lines that we can pick that have different intercepts and different slopes, and one of those lines best fits the data. And we can find the coefficients for that line in R using a linear model function LM. So I can do LM. I first enter the predictor variable, or excuse me, the response variable on the y-axis, followed by a tilde, and then the predictor variable, which is on the x-axis. So it goes y tilde x. It goes response first, followed by predictor, which might be counterintuitive, but we first enter the response, followed by a tilde, and then whatever, you could have more than one, but in our case, we just have one predictor variable, pressure, and then we indicate the data frame, the name of the data frame where these variables are stored. So if I run this code cell, it is telling me that the line of best fit has a y-intercept of about 1,301.7, and it has a slope of minus 1.26, and we should expect a negative slope in this case. So there's our formula. And when we're making a prediction, we put a hat over the variable name. So there's a difference between the observed values that we see. These are values that are marked in as black points. And then the predicted variable from our model is just going to be a unique value. So for each pressure value, we get one predicted wind speed, and that corresponds to the value which is plotted on the line. And so the error of our prediction we can measure as a vertical distance between any observed point and the predicted value on the line. So however, the further these points are vertically from the line, the worse the prediction was and the larger the error is. And the closer these points actually fall to this line, that means the prediction was more accurate. It was much closer to the actual observed value that we have in our data set. So one way that we can find the line of best fit, or how we can define what the line of best fit is we want to find the line through this data that has the smallest error. And that's a complicated thing because we have, in this case, like 20,000 dots in our plot, and they all have different values for the error. Some of those errors are positive. Some of those errors are negative, depending on whether the dots are above or below the line of best fit. And we don't want these negative errors to cancel out the positive errors. So one really common way to find the line of best fit is to consider what's called the residual sum of squares function, the RSS. And so how that function works is we calculate for each observed value of y, we calculate the error of the prediction, which is called the residual, by taking the actual observed value minus the predicted value. And we denote the predicted value again with the hat on top. And since we don't want negative errors and positive errors to cancel out, we think about, there are different ways that you can do this, but one really common way is to square the value of the error. So now all of the errors, when we square them, are going to have positive quantities. And then I add all of the squared errors together, and that gives me a sense of like how large is the error from all of the predictions. And I define the line of best fit as the coefficients A and B that are going to minimize this function, that are going to make the sum of the squared errors as small as possible. And so this is actually, we can frame this question in terms of matrices. And if you're familiar with how regression works and you've solved one of these models before, how that process goes is we set up a model matrix for our system. And so this model matrix, the first column has all ones because for each of these equations, I want to have, I'm going to have an intercept over here. So my general equation looks like this. So each of these is going to have A times 1. So that's where that first one comes in. And then the second column corresponds to all of the observed values of our predictor variable. So I set up this model matrix. The first column of ones is giving me the y-intercept, and then this is giving me the term b times x. And if I had more than one predictor variable, I'll have multiple columns of data over here. But in our case, we have one predictor variable, which is the pressure. So this equation that we had above, the RSS, minimizing that equation can be solved by solving what we call the normal equations, by solving this matrix equation, where X is denoting this model matrix that I have above. And so I take the transpose of X times X, and this is going to give me a square matrix that I can find the inverse of in most cases. So I'm going to take the inverse of the product of X transpose and X and multiply that by X transpose, and then multiply that by the column vector of predictor, of the response variable y. So these are the observed outputs. This would be like a column vector of all of the wind speeds. So I'm going to calculate this complicated product of matrices and vectors, and the result of this product is going to give me the values for the coefficients A and B in the line of best fit. So let's apply this method to our example with storms and pressure and wind speeds. So in this case, we've got wind, and that's going to equal some y-intercept plus slope times pressure value. And what I want to do is find the coefficients A and B for the line of best fit through this data. So I set up my model matrix. Again, it's going to have a column of ones for the intercept, and then a column corresponding to all of the pressure values. I set up my vector of wind speeds of the response variable. And once I have X and Y entered, I can then use matrix arithmetic in R to calculate this product. So that's what I'm going to do in these code cells below. So here, I'm going to column bind. So when I first put a 1 over here, this means it's going to create a column of all ones. And my second column is going to be all of the pressures. So this is going to bind together a column of ones and then end the column vector corresponding to pressure values from the storms data frame. And I'm storing that in capital X. In the vector Y, I'm going to store the response variable wind. I'm going to run this code cell. And again, you want to make sure that you have loaded the dplyr package so that you can access the storms data frame. And these are large matrices. This matrix has about 20,000 rows. So it's huge, but I'll just print out the first 5 rows of this model matrix. So again, the first column is all ones. The second column has the pressure, the observed pressure for each observation in the data frame. Our column vector y is being stored as a vector, and this is just a vector of wind speeds. And now to find the coefficients A and B in the line of best fit, I calculate this product. So I'm going to do that in a couple of steps. So remember, T of X is going to calculate the transpose of matrix X. So here, this first code cell, or this first command, excuse me, is calculating the product of X transpose and X. This next command is going to take the inverse of that matrix. So I've got X transpose X, and then this is going to calculate the inverse. I'll use the dot notation here. So X T X dot INV is the inverse of the product of X transpose and X. And now what I'm going to do is go ahead and multiply the inverse of X transpose times X. So that's what is going here, times the transpose of X, because that's this piece right here. I put that over here. And then I multiply matrix-wise by the column vector Y. So I've stored X and Y above. Running these 3 lines of code is going to calculate exactly this product on the right side. And it gives me a vector that has the coefficient for A and for B. And you can check and compare this to the output that we got from the linear model function, which had the same values. It rounded the slope off. When we solved this by hand, we got more accurate values for A and B. And another way that I could solve this equation, well, I don't have to like break this down into all of these intermediate steps. Once I have X and Y, I don't need to store things intermediately. I could have just calculated that product all at once. And so here's an alternate way of doing it all at once to get these coefficients for A and B. So that is a nice way of showing how you could perform linear regression yourself using matrices in R. These matrices, X and Y here, these had 20,000 rows. So these were really large data sets. And working with these matrices, we were able to find the coefficients A and B in less than a second. These code cells took less than a second to run. But when you're working with really large matrices, these products can take a long time or can be more computationally intensive. So the next video is going to go into some tips about how you might be able to optimize the efficiency of your code when you're working with really large matrices.